Hello, everyone. I would like to introduce my poster to you as part of Project C11, Development of System-Level Distributed Sensing Techniques for Long-Term Monitoring of Concrete and Composite Bridges. Distributed sensors for bridge monitoring provide a better understanding on structural performance and deterioration. A new composite bridge in Hampden, Maine, has been selected for the application of recent developed sensing textile in this joint effort by UML, St. Gobain, UMaine, AIT Bridges, and Maine DOT. This poster describes our preparation for the sensor instrumentation on 3 composite bridge girders. Installation procedure. The sensing textiles are supposed to be installed on the bottom of the girders. Since the girders have a height of about 4 feet and it is already permanently kept on the top, installers are not able to fully stand up while installing. Besides, the epoxy that will be used for sensing textile cannot be cured within a short time. So the area that has already been applied with epoxy cannot be stepped on again during installation. With such limitations, we came up with an installation schematic as shown in Figure 1, where installers will be sitting on a cart to install the sensors in a backward direction. A supply cart will be connected to the installer's cart with a pulley and a rope that is long enough so it can reach to the other end of the girder. By pulling 1 or 2 ropes at the other side, the supply cart or the installer's cart will move accordingly. Sensor integration. A strain gauge system and an optical fiber system using BOTDA are used in sensing textiles. The sensing textiles have the dimensions of 1.5 feet by 72 feet. They are made in a way where optical fibers are firstly sewed onto a fabric substrate by St. Gobain with their patented technique, and then strain gauges will be integrated onto the fabric. Figure 2 to 5 illustrates one integrated sensing textile as an example. Figure 5 also shows how a sensing textile system looks like right before installation. Installation carts. 2 carts were designed and manufactured, installer's cart and supply cart. Surface dimensions of the installer's cart are 15 inches by 3 feet. A mat composed of 4 layers of different thicknesses of sponges is made to make the cart more comfortable to be sat on. The size of the supply cart in Figure 7 is 15 inches by 15 inches. LED lights will be installed on the installer's cart to provide auxiliary light inside the girder, since the installers will also be wearing headlights during installation. On the supply cart, a 2 inches thickness foam with a hole in the center will be glued onto its top surface. The purpose of the foam is to fix the epoxy container during epoxy supply. Bridge girder model. An 8 feet long 1:1 scale mock-up bridge girder model was made with foam boards for the preparation of sensors installation. It was used to practice installing sensing textiles and the design of installation carts. Epoxy effect. 2 strain gauges were used to study the effect of epoxy curing. 1 strain gauge was applied with epoxy on one side, and the other epoxy was applied with epoxy on 2 sides. Figure 11 showed the strain change in 12 hours after epoxy applied on strain gauges. It shows that 2-sided epoxy deployment causes less strain change than 1-sided epoxy deployment. In conclusion, we designed, manufactured, and tested 3 integrated sensing textiles for New Hampden Bridge. We also developed an installation apparatus and a procedure, as well as practicing sensor installation on campus. In the end, I would like to thank the financial support from TIDC, my professor Su-Yang Yu, my teammates Harsh Gandhi, Sandana Vinayaka, and the director of laboratory, Gary Howe, for his help in making the cart. Thank you.